So okay, so this is the Helen's integral differential equation. Differential is outside the integration, so this is Helen's integral differential equation. And you have differentiation also, integration also. That's why integral differential equation. In the Helen's integral differential equation, this operator 1 by j omega epsilon 0 del square by del z square plus beta naught square is outside the integration. But there is another integral equation in which we can take in this operator inside the integration, and that is called Pollington's integral differential equation. So here you can see that the differential operator del square by del z square plus beta naught square, we have taken it inside the integration. So this is called Pollington's integral differential equation. So it's easier to solve it because we can actually do the differentiation of iz, gz, iz dash, gz, comma, z dash. We can do it, differentiation of this, and we can simplify this equation into an integral equation. So this is an integral differential equation. After I do the double differentiation of iz dash, gz, comma, z dash, I can have a simple integral equation, not integral differential equation. I can get rid of this differentiation. So this is called Pollington's integral differential equations. And as I've told you in the last class also, there's a simpler expression for this, where you have get rid of the what is that? Okay. So this fellow Rismond has actually simplified this above equation. He has taken care of this differentiation, and we can simply convert this integral differential equation to a simple integral equation. We'll see that expression later on. Just before that, last class we have discussed this, but it was very quick, so I want to do it properly so that you know what is actually going on. R is the distance between the source and observation point. So R dash is the source variable and R is the observation variable as usual. So if I want to find distance between the source and observation point, I can find it as square root of z minus z dash whole square plus rho vector minus rho dash whole square. So rho vector is basically for the observation point, rho dash is for the source point. So now we are considering a cylindrical structure. So if you are considering a cylindrical structure, the current was actually distributed around the circumference of the cylinder. In that case, what should be rho dash? Rho dash is the source point. Source point, it's always located in the circumference of the cylinder. In that case, what was the radius of the cylinder? A. So rho dash becomes A. So if I want to find modulus of rho vector minus rho dash vector, I can find it out like this. Rho square plus A square minus 2 rho vector dot product with rho dash vector. What is rho? Rho is the distance of the observation from the axis of the cylinder. And A is the radius of the cylinder. And when you do dot product of this is rho vector dot product with rho dash vector. This is basically, what is rho dash? Rho dash, what's the amplitude of rho dash? Amplitude of rho dash is A. So what is the amplitude of rho vector? Rho. So rho A. How about this dot product? It will become cos phi minus phi dash. What is phi? Phi is the angle for the observation point and phi dash is the angle for the source point. So we can find out what is rho minus rho dash, modulus of that, by using this formula. And what we want is R minus R dash, modulus of that. So this contribution here, rho minus rho dash, can give me the second term of this. First term is already z minus z dash whole square. You plug it in. What is R? R is the distance between the source and observation point, and R is the position vector for the observation point. R dash is the position vector for the source point. So we can easily find it out. Square root of rho square plus A square to rho A cosine of phi minus phi dash plus z minus z dash whole square. So here I am making an observation. I can make observation for any value of phi. So without loss of generality, I can make observation at phi is equal to 0. It's not going to make any change in the expression. So in that case, phi will become 0. Phi minus phi dash will become just phi dash. This expression will be simplified like this. Distance between the source and observation point is square root of rho square plus A square minus 2 rho A cos of phi dash. Phi will become 0 now, plus z minus z dash whole square. Then I have told you about the thin wire approximation. No? Thin wire approximation where your radius of the wire is very small. In that case, all the terms which are dependent on the A. A is the radius of the wire. If A is very small, A is very much lesser than lambda. In that case, you can neglect all the lambda A dependent terms, and you can simply write is R as approximately square root of rho square plus z minus z dash whole square. This is a major simplification. So now, how do I find AZ? AZ is simply mu naught integration by 2 to plus L by 2 IZ dash by 2 pi, and 0 to 2 pi is this exponential minus j beta r by 4 pi r d phi dash dz dash. But here, first I want to do the integration with respect to phi dash of this inner term here. So let us concentrate on this term here, inner term here, 0 to 2 pi exponential minus j beta r by 4 pi r d phi dash. So now, R, what is R? R is square root of rho square plus z minus z dash whole square. R is independent of phi dash. So this term here, exponential minus j beta r, not R divided by 4 pi r will be independent of phi dash. In that case, I can take this as a constant, just do integration over d phi dash. What do I get? This is integration is from 0 to 2 pi, so I'll get 2 pi. 2 pi into exponential minus j beta naught r by 4 pi r. So in that case, I can simplify this double integration to a single integration, because this integration I already done it. I'm getting exponential minus j beta naught r by 2 pi r. So I plug it in, then finally what I'm getting is AZ is mu naught minus L by 2 to plus L by 2 IZ dash exponential minus j beta naught r by 4 pi r dz dash. So look at this term here. This term is basically your Green's function for free space. So what I'm doing is convolution of the Green's function with the source current density, then I'm getting the metric vector potential. So I go to metric vector potential, and the Green's function for this case, when you have thin wire approximation, actually converts to that of the free space. Free space Green's function is exponential minus j beta naught r divided by 4 pi r. So now you can write the expression for the Pollington's integral differential equation. After making all the simplification, it converts to a simple integral equation now. So we just have integration here. All the differentiation can be taken care of. And if you are interested, you can look at example 10.4 of the EM theory book I have written. So it has been derived in that example. So I don't want to spend time on the derivations here. If you are interested, you can always refer to the book. So now today's class is once I have this integral equation, how do I apply the integral differential equation? How do I apply the method of moments? So the derivation for the Pollington's integral differential equation was already done last class. I've just revised it now. And this is a simplification. It becomes an integral equation. We'll use it later on in another example. So the question is, how do I apply MoM to solve the unknown current density here? So how do I apply MoM to solve the unknown current density here? Once I have the unknown current density, I can find all other antenna parameters. So we are considering a dipole wire antenna. So we want to find the radiation from dipole wire antenna. So if I want to find the radiation from the dipole wire antenna, I need to know the current distribution on the dipole wire antenna first. So now I can apply MoM to solve the unknown current density on this dipole wire antenna. So what was the first step? First step is you apply the linear approximation of the unknown function in terms of some known basis function. And we have discussed about some of the popular basis function, subdomain basis function in the last class. One is pulse function, one is triangular function, one is sinusoidal, piecewise sinusoidal function, piecewise triangular, and the pulse basis function. We have already used pulse basis function also in the last class. So we'll use the simple pulse basis function here again to approximate the unknown current density Ij dash in terms of basis function In, Bn, Z dash, n going from 1 to capital N, where Bn is a pulse function. Pulse function is actually defined over the interval delta Zn dash. Over that interval, pulse function will be 1, and outside that it will become 0. This is the wire antenna, dipole wire antenna. Dipole wire antenna has upper arm, then lower arm. We are doing the discretization of this dipole wire antenna into small segments here. So one segment, we are making many segments here. And after discretization, we want to find the current density in each and every segment of the dipole wire antenna. So if I know the current density in each and every segment of the wire dipole antenna, I can combine it. I can plot the current distribution for this dipole wire antenna. So this is a discretization, we are doing it. So this discretization size is delta Zn. See, how much is this from here to here? Every discretization along the z-axis dimension is delta Zn dash. So that's a notation. Okay, so what is this point here? This point here is the source point. So you know that current was, see, it's a hollow conductor, so current was flowing on the circumference of the wire conductor. So this is a source point for the current. Where is our observation point? I can put my observation point anywhere, but I don't want to have that singularity effect. So let's say we consider this segment, and if I put the source and observation at this same point, I will have singularity effect. The integration will become infinite because distance between the source and observation will be 0. So I will intentionally displace the observation point from the source point. So I will make an observation along the axis of the wire. So this is one observation point, any arbitrary observation point M, Zm. This any arbitrary will denote it as Zn dash is the source point. With the dash is the source point. So this is just a notation. No? So it doesn't mean that it will have only variation over Z. Just a notation. Zn dash means this location here. Zm is this location here. So now most of the time I have the distance between the source and observation point. For this particular case, the distance between the source and observation point is Rmn. So this is the mth point, observation point. This is the n dash, nth source point. Distance between them is Rm dash. That's how I find the distance between the source and observation point. So let's say if I have a source here, I want to observe the current density here. Then I need to know what is Rmn, distance between the source and observation point. If I have a source here, I want to know the current here. I need to find the distance between these two. Similarly, I will have to do it for every segment. So whenever I have a source here, I will find the distance between the source and observation point for every segment. So similarly, I can even change this position of the source here. Then I can again find the observation, the current density over all segments. That's why we have a matrix. So one source will give you one column or row of the matrix, but when you have source at all points, you will get a matrix. So now let us find out what is the length of the nth segment. So nth segment is starting from here and it's ending here. So the point we have considered is the center of this. So nth segment is starting from here and it's ending here. So what is this point? This point is L by 2 minus L by 2, and this is L by 2. We usually denote the length of the dipole is L, and start from minus L by 2 to plus L by 2. So if I want to locate this point here and this point here, then I need to find like this. So if I want to find this, so I start from minus L by 2, then what's the size of the subsection? Capital L by capital N, and we are at the nth segment, so it will start from n minus 1 to n. So this is the segment, minus L by 2 plus capital L by capital N, n minus 1. Is that okay? Z is varying from this point to this point. This is what we are finding here. Location of this point here. So this is minus L by 2. This is the nth point. So this will start from n minus 1 L by 2. This will end at minus L by 2 plus capital L by n into small n. So this is what L by n, and so this is the segment we are considering. Nth segment will have this value range of value for Z. So this was the equation, convex notation of the equation. This is the incident field, this is a scattered field. So this is a IZ is the current density, FZ, from FZ we can find out the Z matrix. From here you can find out the B matrix. FZ was like this for the Pollington's equation, 1 by j omega epsilon. This is the operator which was inside the integral sign. So this is the Green's function. So now we can substitute IZ dash in terms of the pulse basis function, and let us assume that the testing function is the delta function so that we can get rid of the integration. So what is the location of the segment M, center of the segment M? So what is the location of center of segment M? This is observation point. M is the observation, N is there are two running variables here, one for the source, one for the observation. For the source we are having N as a running variable, for the observation we are having M as the running variable. So we started from minus L by 2, then L by 2, M minus half, because this is the center. Let us look at the diagram here. This is minus L by 2, and we are finding the location of this center. What was this point here? This point was minus L by 2 plus capital N by capital N, that is the size of the subsection, into M minus 1. But here, this is at the center, M minus 1 plus half. So that's why we have here this location. Just we need to worry about the location of the source and observation point. So capital L by 2, M minus half. That is the center of the Nth segment where we are observing the current density. So now the equation becomes this when we are observing at the center of the Nth segment. The previous equation simplifies like this, and we have also taken care of this term here. This IZ dash will replace it by summation IN BN dash, and this summation is independent of the integration. I can take it outside. So summation n going from 1 to capital N, IN BN. BN is having a value of 1 only over this interval, delta Zn dash. Outside that it's 0 because Bn is a pulse function. That's why this integration is over the range of the delta Zn only. So outside that it's because we have Bn here, and we are also making an observation at Zm. So finally you can write the equation like this: left hand side, right hand side. This whole term, integration term, I will just denote it by F and N. And what was our testing function? Testing function was a delta function, so I can simplify this expression and finally write down this by using the centroidal approximation. I just find this function at the center and multiply with the length of the interval. So this is by using the centroidal approximation. So we don't have any integration now. Integration has been taken care of by the centroidal approximation. So we can find out F and N. We also know how to find it out. This one, we can find out IN. You can find out the, once you have IN, then you multiply with BN, then you get the unknown current density. So sometimes people actually, this is electric field here. So we are interested in finding B matrix. So we usually multiply by delta Z both sides. Here also you multiply by delta Z. Here also you multiply by delta Z. And write this F matrix as Z matrix, and write this E matrix as B matrix, so that you know it comes to the same equation we have started for the MoM. MoM is Zi is equal to B. So just multiply with delta Z in both sides, and you can express this in terms of Zi is equal to B. So once you have the current distribution on the thin wire dipole, you can find out all the antenna parameters. We have done this analytically also. Once I know the current distribution, I can find the electric field. Once I have the electric field, I can find all antenna parameters like gain, directivity, all those antenna parameters. Just before that, let us find out the input impedance at the center of the dipole antenna. So dipole is fed at the center. You have an upper arm of length L by 2 and lower arm of length L by 2. If I want to find out the input impedance at the center of the dipole, how much was the voltage we were applying at the center? It was 2V0. And what was the current at the center? Current at the center will be IN by 2 into Bn. Bn is anyway 1 over that interval. So if you know IN by 2, that is the current at the center of the dipole, you divide with the voltage you are applying. You are applying voltage of plus V0 and minus V0 over the upper arm and lower arm. So you can find out 2V0 divided by IN by 2. You get the input impedance of the dipole. You can also find out the total radiated field. It will compose of incident field. Incident field is already known to us, and you can also find out scattered electric field now once you know what is IN. IN is the only unknown in this expression here. Bn is known. All other terms are known to us. So you can find out the scattered electric field. You know what is incident electric field. You can find out the total radiated field also. Okay, so let's take a simple example. So let's take a simple example to illustrate what we have learned. Let's consider a short dipole, very short dipole, thin wire dipole, and radius of the thin wire dipole is 0.01 lambda. So it is much more lesser than the lambda. So 0.01 is 1 by 100 of lambda. So it's a very thin wire dipole. I can use thin wire approximation. Green's function will become Green's function of the free space. The total length of the short dipole is simply 0.3 lambda. And I want to use MoM to find the current distribution on the short dipole. And I also want to find out the input impedance of the dipole antenna, so that if I have a coaxial line, if I know what is the input impedance of the dipole antenna, I know how much is my reflection coefficient. ZL minus Z0 by ZL plus Z0. ZL is the input impedance of the dipole antenna. So once I know that, I know what is the reflection coefficient at the feed point of the antenna. So this dipole antenna is a one-port device. If I know what is reflection coefficient at the input point, I know I can also find out what is the bandwidth, all these parameters. So S11 is the parameter we need to find, which is basically the reflection coefficient at the input point of the antenna. So that is a port 1 of the antenna. So we can find out the scattering parameters once I know the input impedance of the antenna. You can assume the frequency of operation is around 1 megahertz, and the number of subsections on the wire is only 3. So if it is a 3 segment, we'll have 3 by 3 matrix. So things become very simple. So Z matrix will have only 9 components, 3 by 3 matrix, Z11, Z12, Z13, and so on. This I vector will have I1, I2, I3, B1, B2, B3. So if I want to find what is the input impedance, I need to know what is I2. I know what is the voltage I'm applying. If I divide voltage divided by this I2 here, I can get the input impedance of the dipole antenna. So now you know that this Z matrix is simply multiplication of delta Z with the F matrix, and E matrix is multiplied with delta Z, you get a B matrix. So let us try to calculate this. So Z matrix expression, again, it has been simplified in the book, example 1.5. This is the expression for the Z matrix. So look at this Z matrix expression. What do you have? ZMN. No? You have JZ0. This is the free space wave impedance. Delta Z is the step size. Now, when I have a dipole of length 0.3 lambda, if I have only 3 subsections, how much should be delta Z? Delta Z will be 0.3 lambda divided by 3, so 0.1 lambda. That will be the delta Z. So lambda is known to us because frequency is given. Once you have frequency, you find the ratio of speed of light, which is 3 into 10 to the power 8 divided by the frequency, you get the lambda. Frequency was 1 megahertz, so I can get what is delta Z, I can get what is lambda. And I also have Rm, and A was also given. A was the radius of the cylinder, which was 0.01 lambda, 1 by 100 of lambda. So the only unknown parameter I need to calculate here is Rmn. So once I have Rnm, I can find out Zmn. There is no integration. We have taken care of the integration by applying the centrifugal approximation. So Zmn has the simple expression like this. Here, the only calculation I need to do is Rmn. Rmn, R11, R12, R13, and so on. So let's do that calculation. For the thin wire approximation, Rmn is square root of rho square plus Zm minus Zn whole square. So now if I have R11, then source and observation are at the same location. In that case, this will simply become A. A is 0.01 lambda. So I have the value of R11. What is R12? In R12 case, what is the distance between the source and observation along the z-axis? Distance would be delta z. This from one segment to another segment. How much is distance? Delta z. So you have square root of A square plus delta z square. You know what is A, you know what is delta z. Delta z is 0.1 lambda. A is also 0.01 lambda. You can find out it's approximately 0.1 lambda now because this is very small anyway. A is very small. So this becomes 0.1 lambda only. Similarly, R13 also you can find out what is distance between Zm and Zn. Distance between the Zm and Zn is 2 delta z because this is for the first segment and third segment. So you find out R13 it is 0.2 lambda. And you know that obviously distance between 1,1 and 2,2 and 3,3 would be equal. And distance between R12 and R21, R23 and R32 should be equal because this is one segment apart. No? This is two segments apart. This is at the same segment. You are finding this distance between the source and observation point. You have all values of R11, R12, R13, and so on. You can find out the Z matrix now. Again, this Z matrix is a symmetric perplex matrix. You just need to find the first row, Z1, Z2, Z3. Then you just make a rotation. Start from Z2, Z1, Z3, Z3, Z1, Z2. So first row start with Z1, second row start with Z2, Z3, Z1. Circular rotation. Then again, third row will start with Z3, Z2, Z1. It's again circular rotation. So you just need to find this first row. You can fill up the second and third row by doing a rotation. So you don't need to do too much calculation. And you know how much is the voltage you are applying. At the center, we are applying a voltage of 1 volt. And in the, see, basically we have done subsection of the thin wire into 3 parts. First part, second part, and third part. Only the middle part we are applying the voltage. Above part and lower part, which is basically in this case is upper arm and lower arm of the dipole, we are not applying any voltage. Voltage fit gap. No? So at the gap between the upper arm and lower arm, we are applying the voltage. So if you apply voltage of 1 volt, B matrix will simply become 0, 1, 0. So I have everything now. I can find out what is the I matrix. Z matrix is known to me, B matrix is known to me. So I inverse, Z inverse B will give me I matrix. From the I vector, I can get what is I2, then I can find out what is the input impedance. Once I have I1, I2, I3, I multiply with the pulse function B1, B2, B3, I get the unknown current density. So this is a very simple process. Is it okay? Any questions? Okay, so let us have a discussion on the choice of software language. So most of the time, for the computational electromagnetics, people use Fortran as a programming language because it's very fast and efficient, very fast. When you write your program in Fortran, when you try to run it, it will be very fast. So that's why from the very old days, maybe around 100 or 50 years back also, people has been using Fortran language. But around 25 years back, Fortran was a functional language. You have two kinds of language. Programming language, one is functional language where you write all the programs in terms of function. You define the program in terms of function, many functions. So Fortran was like that. So when we learned Fortran, maybe around 20 plus years back, 25 years back, Fortran was a functional language. And we usually call at that time Fortran 77. We learned Fortran that there was a functional language, but later on, you have another language which is called object-oriented language, object-oriented programming, where you define all the, in the program, you'll define an object and define its properties. So previously, when you have C is a functional language, C programming language, where you define inside the program different functions and try to implement what you want to achieve. So here in the object-oriented programming, you define an object first and define all its property and do the programming. This is a very efficient programming language, object-oriented programming language. It's even better than the functional programming language. And Fortran, when we learned it around 25 years back, it was a functional language and it was called Fortran 77. Nowadays you have Fortran 95, which is an object-oriented programming language. And you also have C++, Java, all this programming language are object-oriented language and very efficient, very fast, very good to, I mean, when you program it, it's quite easy because you define an object and define its properties, you know, in terms of functions. So if you want to select a programming language for computational electromagnetics and you want to develop a general purpose program, you should not actually stick to the MATLAB program. You should actually go for any object-oriented programming language like C++, Fortran, or Java. But for educational purpose, we use MATLAB most of the time because what are the advantages of using MATLAB? In the MATLAB, it actually accepts complex number. Let's say you use C programming language, you will have to define your own complex numbers. You have to define another function which will actually implement what are complex number. But in MATLAB, complex number is already inbuilt. You can directly enter it, and you can easily create graphics also. So that is one of the major advantages of MATLAB. You can create graphics quite easily using the readily available programs. So most of the time we'll use MATLAB, but let's say nowadays you are very much worried about your job prospects, you know, later after you finish your MTech, you want to get job, you know, you can even explore programming language like C++, Java, or nowadays you have Python language, all this. See, if you want to write your assignments, programming exercise in terms of object-oriented programming language, you are most welcome, huh? Because that will actually help you in your, you know, later on when for your placement. So these programs you can even write in object-oriented programming language, so that, you know, when you learn computational electromagnetics, you also learn object-oriented programming language, and it will help you because nowadays most of the jobs you get after you do your MTech would be on programming, you know, software profile. So, and one of the major disadvantages for MATLAB is for loop. You can always check that. You just write a program, MATLAB, short MATLAB program, and you put for loop once or twice, and you see how much is the runtime. Runtime actually runtimes increase abruptly. It will take a lot of time. So try to avoid for loop in MATLAB. It takes a lot of time. So you can use any programming language and do your assignment. MATLAB is one of the options, but you can also use any object-oriented programming language and do the assignment so that it helps you in the future job prospects. It's your choice. Now, I don't have an issue in any programming language you choose. I have not learned Python, but I have learned all the programming languages. I was a software engineer for almost 1 year. So there was an induction program where we learn all the software programming language. So I have knowledge of all the programming language except Python. At that time, Python was not there. It has come later. So you can choose any programming language. I have given MATLAB as one of the choice, which is easy for everyone. But if you want to explore any object-oriented programming language, write your code, you are most welcome for any programming exercise. Okay, let us summarize the steps of the MoM so that you can use it for electrodynamic case. We have done it for electrodynamic also, we have done it for electrostatics also. Let us just summarize what are the 3 important steps for method of moments. First thing is you have to derive the appropriate integral equation. We have done that for electrodynamic case, also electrostatic case. First, derive the integral equation. That's the first step. Second step is you convert this integral equation to a matrix equation. How do you convert it? By applying basis or expansion function or weighting or testing function. 2 steps for converging the integral equation to a matrix equation by using basis function and weighting functions, or you also call this as expansion function. Next step, once you evaluate this matrix, then you find the unknown function, and from that you actually find the desired parameters. From the matrix equation, you find out the unknown coefficients, and once you have that, you can find out the unknown function. Once you have the unknown function, you can find all the desired parameters. For example, for antenna, you can find the unknown current density. From there, you can find out the radiation patterns. From the radiation pattern, you can find all other antenna parameters. So this is a 3-step process. First, find the integral equation, then you convert the integral equation to a matrix equation, solve the matrix equation, and find the desired parameters. Okay, so this is a programming exercise we usually discuss in the class. So what I usually do is I show this exercise in the class, then students write their own program in the class. But now this is an online class, so I'll briefly discuss it, so we won't be able to do that. So in this programming exercise in the class, you assume a fit at the center. This is a dipole. This is a dipole, but we'll solve it for electrostatics, not for electrodynamic case. We'll solve the current distribution on a dipole for electrostatic case. So assume the radius of the cylindrical dipole is A is this, length of the dipole is 0.05 meter. These are the epsilon 0, you know what is 8.85 into 10 to the minus 12. What is epsilon r? Epsilon r for here is 1. And let's assume that number of segments is 30. We'll use that many pulses. Then what should be the delta Z? Delta Z would be total length divided by the total number of segments. Total length is 2L, 0.005 meter divided by total number of segments. What is the match point? Location of the match point is, you have already done that, similar to what we have done now. So M minus 0.5 delta Z minus L. So total length of the dipole now is 2L. That's why we have minus L here. Previously we have total length of the dipole was L. That's why we have minus L by 2 here. And for the electrostatic case, Z matrix will have, this is the diagonal term and this is the off diagonal terms. You can find out the diagonal term from this M is equal to N, of diagonal term from this M not equal to N. Then you can create this matrix. You can create this matrix. So ZMN is given for you. ZMN is given for you. Just need to find it out. What is delta Z? That's the size of segment, that is 2L divided by capital N. You know what is delta Z. What is radius of the cylinder? You know it. And what is Zm and Zn? The location of source and observation point. You know it. From there you fill up this Z matrix. Then let's say we are applying a voltage of V0 of 1 volt. See, basically we are applying a voltage of V0 1 volt at the center of the dipole, and we want to find the charge distribution of the dipole. Then Dm will become this. So this is a matrix. I vector would be inverse of Z matrix with the B matrix. I know everything. I know this. I know this. What is B? B is 4 pi epsilon 0 epsilon r B naught. I know this. I know this. I can find out I1, I2, I3, and up to I30. From there, I can plot the line charge density on the dipole. This is an electrostatics example. This is what in the offline classes the student will write this program on a piece of paper and show it to me, and they can even bring their own system and write and run it and see. But now that's not possible, so I have discussed it. That's a very simple program. So this is the next assignment, programming exercise 3. I've already got programming exercise 1 from many of the students. Those who have not submitted, try to submit it today. So this is the programming exercise 3. Okay, so here we will try to solve the Pollington's equation, Riemann expression, very simple expression. Riemann has this. Here we don't have any differentiation. It's an integral equation now, Pollington's equation. So now this equation you have to solve it to find the current distribution and input impedance of a center-fed dipole. You have a dipole upper arm and lower arm. It's center-fed. You want to find the current distribution on the dipole using this Pollington's equation. In the Pollington's equation, you have the unknown current density. You can find it using the MoM. So we'll use piecewise constant function. That's the first function. Excitation will use a better excitation here. I will discuss that later on. Magnetic field source. We have done delta gap excitation where you put voltage B plus in the upper arm and B minus in the lower arm. But here we'll have another better excitation which is called magnetic field source excitation. And matching is point matching, delta function. So now how do you write this program? So first, when you write this program, see, I will tell you step by step how to write this program. First thing you need to do is you have to define Z coordinate as symbol variable. No? So if you define any variable as a symbol, you can do integration, because here we have integration. So that's why I have defined Z as a symbol variable. Then you have radius of the dipole is given. A is this outer radius of the coaxial cable. Actually, dipoles are fed by coaxial cables. So those who are doing lab experiment, they know that all the antennas are connected with the coaxial cables. So those who are not attending the lab, I think maybe one or two students, if you are not following what I'm telling you now, you can always discuss with me after the class also. So we usually replace all the wires by coaxial cables at the microwave and optical frequency. So the source signal would be coming through the coaxial cable. So coaxial cable would be the input line. From there, source signal will be coming. It will be connected to this cylindrical dipole. So now, inner conductor of the coaxial cable would be connected to the dipole antenna. Outer conductor would be grounded. So the radius of the outer conductor is this. Radius of the inner conductor is this. The length of the dipole, half wavelength, is 0.05 meter at frequency of 1 GHz. Speed of light is 3 into 10 to the power 8 meter per second. You can define this at the beginning of the program. And epsilon 0 is this, epsilon r is 1 for air, and epsilon r is 2.03 for Teflon. See, basically in the coaxial cable you have an inner conductor and outer conductor. In between the inner conductor and outer conductor, you have a dielectric medium. So that dielectric medium is usually made of Teflon, and epsilon r for that is 2.06. Angular frequency omega is 2 pi f, k is 2 pi f square root of epsilon r divided by c. This is a propagation constant. Let us assume that number of segments is just 9. I have taken an odd number so that I can find the center, and from the center I can find out what is the input impedance. So segment length will be 2h divided by n. What was 2h? Half length dipole. So 2h will be this multiplied by 2 divided by total number of subsection is 9. So you can find out what is delta z. What was the match point? Match point was m minus 0.5 delta z minus h. Total length of the dipole is 2h. M can vary from 1, 2, 3 up to 9 again. So this is the expression for the Z matrix, Zmn. 1 by 4 pi, you have integration over the interval. Nth interval is from Zn minus delta Z by 2, Zn plus delta Z by 2. This is the expression, Riemann expression. What is Rm? Rm is square root of a square plus Zm minus Z dash whole square. Zm is the observation point, Z dash is the source point. So depending on different value of Z dash, Z1, Z2, Z3, you can have Rm1, Rm2 and so on. This you need to calculate. This you need to integrate. If you have defined Z as a symbol variable, then you can do integration of this. You can use a command quad b function in the MATLAB toolbox to do the integration. And you can even use integral also. Integral 1D integration, you can use integral 2D integration, you can use integral 2 also. You can explore. So just find out this first row of this matrix, then you can find out all other rows. So this first row you are finding. So here we'll find out upper triangular part of this matrix. Then I'll make a trick. I don't need to find the lower triangular matrix. If I find out this upper triangular matrix, I take a transpose of this upper triangular matrix and sum with this. So let's say this is A matrix. I take transpose of A matrix and sum with the A. So A plus A transpose will give me the actual Z matrix. That's why I have put a divided by 2 here. So diagonal terms will add up. Of diagonal terms, upper triangular will be there. When I take transpose, this will be here. So I can find out the matrix. I don't need to calculate the whole matrix. So what is this magnetic field source excitation? Here, your feed gap is replaced by a circumferentially directed magnetic current density. So along the circumference of the cylindrical dipole, you assume that there is a magnetic current density flowing. Because of that, you can find out the electric field. That's how you find it. If you are interested, you can explore this. I have given a link here. You can read this paper. It has given a very good description of this magnetic field source excitation. But for us, we just need to know what is EZ. EZ for magnetic field source excitation is this. This is basically the electric field. You can find it from the electric field of a coaxial cable line. So coaxial cable line will have outer conductor and inner conductor. So you have R1 and R2. One for the inner conductor, and this is for the outer conductor. This is the electric field exponential minus jk r1 by r1 minus exponential minus jk r2 by r. You can easily find it out. This looks like the electric field of a coaxial cable. A is the outer inner conductor, B is the outer conductor. From there you can find out what is Ez. So once you have Ez, you have everything now. You have the Z matrix, you have the Ez matrix. You can find out I matrix as inverse of Z matrix with the Ez matrix, and you know how much is the voltage you are applying at the center. So now we have 9 subsections. Center is at I5. So I know how much voltage I'm applying. 1 volt. 1 divided by what is the value of I5 I get from this. I can get the input impedance of the dipole. I think that is good enough for this class.